So, yeah, I'm very happy to be here, and I would like to thank all the organizers for inviting me. I mean, I know everybody says that, but I really mean it. I'm seriously happy to be in Cambridge, which I found very nice environment, very inspiring, and so on. So the topic I'd like to tell you about has to do with hyperbolic geometry in liquid crystalline interfaces, and it's kind of, this project has a rather strange story, because it started in 2009, and back then I was a graduate student at Syracuse University, and in fact I was about to leave Syracuse because I had defended my thesis already, and I had a month of time to kill. That never happened again, by the way. And so I came up with this idea, and I tried to do some calculation all by myself, and a month after, I moved to Boston for my first postdoc. And so for 3 years, I've done a lot of interesting things, but nothing that's to do with that, until the very end. A couple of months before leaving from Harvard, and from the US, in fact, I managed to resume this project, finish up some calculation, and publish this paper that came out in 2012, but tells the story that started 3 years later. And for 3 years, I was like, kept my finger crossed to hoping that nobody would have done the same thing. Before getting into the gory details, and there will be some, I'm afraid, I'd like to make some historical remark, about shape optimization in physics and in mathematics. And the reason is that history was really the only motivation for this project. Typically, you start the talk by talking about, cooling, technological application. There is none. Here it was really only history. So a very classic problem in physics and in mathematics is the following. Given a physical system, we would like to find the optimal shape, And the way this goes is generally like this. I mean, you start with an idea of your physical system, the solid, the fluid, whatever it is. Then you have to convert somehow this idea into a function or a functional, if the system is continuous, that represents the total mechanical energy of the system. And then what you try to do is to minimize this function, with respect to some geometrical parameter, and find the shape. I've done this loop many times, actually, and I know I'm in good company here. There is another problem which is more challenging, and it's the inverse one. And in the inverse problem, you don't start from a physical system, but you start from a shape, And then you ask yourself, what is a physical system, a simple physical system, whose lowest energy configuration is going to give you the desired shape, It's never formulated this vaguely, typically, but this is more or less the rough idea. And so the first thing that you have to do is try to guess a physical system, say soap, for instance. And then once you're at this point, which is the most difficult one, then the rest of the flow chart is the same of the direct problem. You solve the variational problem, and then you check whether you're right or not. I didn't make the example of soap by chance, but because in my knowledge, which is limited, of course, the first inverse problem of this kind was actually the plateau problem. The plateau problem on soap films. And the plateau problem was actually formulated by Lagrange in 1760, and they had nothing to do with soap films and soap bubbles, In Lagrange formulation, it was a completely a mathematical problem dealing with surfaces and lines. And this is like, the definition, maybe using a more modern terminology. Given a simple closed curve C, we would like to find the least area surface spanning C, And Lagrange was one of the pioneers of calculus of variation, together with his mentor Euler. And so, using these techniques that he developed, he was able to prove a fundamental identity, meaning that these minimal surfaces, regardless of the shape of the boundary, do match an important condition, meaning zero mean curvature. They have the mean curvature is equal to 0. And in fact, now with modern language, we call minimal surfaces all the surfaces having 0 mean curvature, regardless of whether or not they actually solve a variational problem. Plateau arrived almost 100 years later, And he really did solve the inverse problem, meaning he was able to demonstrate that Lagrange minimal surfaces do occur in nature in soap films, And the reason now, it's simple to explain. The energy of a soap film is proportional to the area times the surface tension. And so for a soap film, minimal energy means minimal area. It wasn't simple back then. This problem then, it originated a lot of important works in geometry, mathematics, in the theory of harmonic functions, and so on. And the existence of the solution is very non-unique, of course, but the existence was proved in the 30s by Rado and Douglas, okay, independently. And Jesse Douglas won the first Fields Medal ever awarded for this achievement. And there are some interesting stories about these two fellows when they proved the solution of the Plateau problem, the existence of the solution of the Plateau problem. Douglas was at MIT, Rado was at Harvard, and they never talked to each other. Okay, things haven't changed too much in Cambridge, Massachusetts. And another story, which I find extremely impressive, is that this guy, Rado, before getting to Harvard, he escaped from a prisoner camp in Siberia during the First World War and walked for over 1,000 miles to get back to his own country. So, sometimes I imagine Rado, walking and trying to somehow, relieve the pain, the physical and mental pain, by thinking about soft films and things like that. All right. Now we know that Lagrange zero mean curvature condition is only the tip of the iceberg, right? And is like the specific realization of a more general force balance condition, which is the Young-Laplace equation that relates the mean curvature of a surface of an interface with the pressure jump across the interface itself. And if you ask me, okay, I'm a low energy guy, I really don't know much about the relativity and the Einstein equation and so on. This is as good as it gets. Because here you have like a very simple formula, a very elegant formula that relates geometry and mechanics. Okay, and this is really extremely beautiful and very profound. And in addition to that, the Young-Laplace equation, the Young-Laplace phenomenon, I would say, is really like the morphogenetic force that you can use to construct a lot of beautiful interfaces. For instance, you can make droplets. Okay, so a sphere that has constant mean curvature and constant Gaussian curvature as well. You can make various kinds of constant mean curvature surfaces of both negative and positive Gaussian curvature. And if you are William Irvine, then you can cover this surface with colloids and study, perhaps, topological defects on curved crystals. And then you can make various kinds of minimal surfaces, including polyhedra. I mean, a polyhedra is like a peculiar kind of surface. This is like developable almost everywhere. If you are Ray Goldstein, you can even make a non-orientable minimal surface like this beautiful Moebius strip, minimal Moebius strip that he used to study transition between surfaces having different topology. Now, it seems to me that using capillarity, you can make almost at least one example of any special surface I know of. At least one family, okay? This. Or this. So constant negative Gaussian curvature surfaces, like the pseudosphere, like, if you're familiar with those guys, those are much more complicated, the Dini surface, the Cohen surface, and so on. So I'm not aware of any system that spontaneously form a surface of constant Gaussian curvature, of interface at least. In fact, not even a solid. These surfaces also have like a very rich history, okay? They have been discovered by Beltrami in 1868. Beltrami was able to understand that these surfaces of constant negative Gaussian curvature provide an embedding of the hyperbolic plane in our three-dimensional Euclidean space, okay? And in the process, he discovered the pseudosphere. And after that, this topic was subject to an abundance of theorems in mathematics. Some of them are very important and very deep. Like, for instance, you may know the Hilbert embedding theorem that says, the surface cannot have constant negative Gaussian curvature, be complete, and simultaneously be regular. Okay, C2 regular. So that's why they all look like kind of cuspy, kind of edgy.
Was he trying to do that experiment with his hand?
Sorry, say again?
Was he trying to do the experiment with his hand?
Who, Hilbert? Oh, yeah, of course. In fact, you see the wrinkles, right? And Nash proved perhaps an even more profound theorem, the famous C1 embedding theorem that says, if you're not as greedy as Hilbert, but you require a much more modest C1 continuity, then you can bet everything you want, and that's going to be complete.
So just to be clear, so this pseudosphere has a measure on the boundary between the two, where
indeed is a, yeah. And you can say that this what is it? Yeah. You can say this is not regular because the tangent vector is continuous, but the normal is not.
How does that tangency occur?
How did the tangency of the two things occur? I don't really know. I mean, this is just, I mean, you take the tractrix and then you revolve it around his axis, and I'm not exactly sure what happens here. I mean, I think at this point, really nothing is really defined. I mean, you can define the limit though. I mean, you can calculate the curvature almost everywhere until here, and then you can calculate the limit as you move in this direction, and still the curvature is well defined. It's not defined at the edge. All right, so this is the problem, okay? Now let's go back to 2009. I had this month of time to kill, and so I asked myself, is it possible to make a fluid interface that spontaneously forms a surface of constant negative Gaussian curvature, okay? And the answer is yes, and it's a liquid crystal. And this is why I'm here. So, so for the remaining of this talk, I would like you to consider this functional, okay, which is, you know, in my understanding, the simplest model for an interface with liquid crystalline order. Okay, it contains two terms: a surface tension and a very, very simple Frank free energy. Okay, here n is like every vector field, kappa is an orientational stiffness, and really I'm not telling you anything about the symmetry of this liquid crystalline phase. Okay, this is all embedded in this director. So this could be a polar, you know, liquid crystal, could be an amatic liquid crystal. Being an amatic liquid crystal, maybe this is a bit oversimplified, okay, because, you know, there are different constants and so on. Could be an exotic liquid crystal, and in fact, as an exotic liquid crystal, this expression is actually very accurate. But the important thing is that the system described by this energy is geometrically frustrated, okay, in the sense that Vincenzo addressed. Geometrically frustrated means the following. Here we have two terms in competition with each other, right? One is a surface tension, and the surface tension is trying to minimize the area of the surface as much as possible at the expense of creating Gaussian curvature, increasing the Gaussian curvature, okay? And the Gaussian curvature is going to make the liquid crystalline phase unhappy, because on a surface having non-zero Gaussian curvature, there is no such thing like two parallel lines, okay? Things have to splay anyway, have to deform anyway. So, you know, the fact of having a Gaussian curvature inevitably is going to distort the liquid crystalline phase, okay? And this is also going to cost energy. Eventually, they will compromise on something, okay? On what are they going to compromise? Let's do some dimensional analysis, okay? So there are two parameters. One is sigma, and sigma has dimensions of energy over area. The other one is kappa, and kappa in 2D has dimensions of energy. And so the ratio sigma over kappa, let's take a minus sign here, has dimensions of Gaussian curvature. So we can expect, just from dimensional analysis, that we are going to obtain a surface whose Gaussian curvature is roughly given by this ratio. And this is actually exact, okay? It's not an approximation. This is exact. And so in the remainder of this talk, I will try to somehow walk you to the proof of this result. Now, it's not going to be like a rigorous proof because I'm going to skip all those steps. In addition, maybe you will find it very boring, you know, in some extent. Well, I'll do my best to deliver that as clearly as possible to everybody. Okay, so this is the program. Now, we want to minimize this energy. And by the way, in doing so, I'm going to make large use of this formalism, these tools of orthonormal frames on curved surfaces that goes all the way back to Cartan, I believe. And in the theory of membrane, at least, you know, the famous paper is this one. It was used to describe exotic membranes in this 87 paper by Nelson and Pelliti. And if you want to learn about these techniques, this paper by Vincenzo Vitelli and David Nelson, 2004, is extremely beautiful, rich, well done, and there are a lot of details. Okay, so it was a constant reference in this work. Yeah, please.
Quickly clarify, what is N here? Is N directly on the surface? Is it a normal to the surface?
No. So, good question. Thank you. So n is a tangent vector on the surface describing the preferred direction of this nematic or liquid crystalline phase.
You're minimizing over the shape of the surface and the director field.
Precisely. So exactly. So what I'm going to do is to minimize both with respect to the orientation of n and to the shape of the surface. Okay. All right. So the first step is that since we are dealing with this vector, we need to introduce like this orthonormal frame. Let's call it E1 and E2, and n has a simple expression like in Euclidean space, cosine theta, E1, sine theta, E2. Now, E1 and E2 is a local base, so moves as you move along the surface, right? Okay. And that's a very important property. If you take the square gradient of n in this basis, in this frame, okay, this is going to be equal to the grad of theta, of this orientational angle, okay? The orientation now is a local one, minus some vector field A. Now, this vector field A is called spin connection, can be defined in this way, and is really like what contains the geometrical frustration in this problem, okay? And the reason is that the curl of this vector field is equal to the Gaussian curvature of the surface. Why this contains the geometrical frustration? For the following reason. Because looking at this expression, you would say, haha, but you can have a zero energy state here if the grad of theta is equal to A. Why not? Because the curl-free vector field grad of theta cannot be equal to A whose curl is non-zero on a surface having non-zero Gaussian curvature. Okay, I don't know whether this is clear. I mean, okay, this vector field is curl-free. This one is not unless the Gaussian curvature is 0. So they cannot be equal to each other.
But this is a covariant gradient.
Yeah, exactly. So all my operators are covariant, are calculated with respect to the metric of the surface. All right, very good. So, okay, so the next step is a simple exercise. You have to minimize with respect to the orientation by taking a small displacement. If you calculate the linear variation, you end up with the following expression. So the first term gives you the variational equation, the bulk term, okay, and this is actually very similar to the one that we have in liquid crystal on the flat space. On the flat space, you don't have such an A vector, and therefore the Laplacian of the orientation is equal to 0. From the boundary term instead, you get the boundary condition, all right? So the boundary condition can be fixed, prescribed. You can have like, an assigned orientation on the boundary, okay, in which case the variation itself is 0, and therefore this term is going to be 0, or it can be free. And if it's free, this requires a further condition, this to be true at the boundary, okay, in order for the variation to be 0. And nu here is this vector that is tangent to the surface and normal to the boundary. Okay, if you are familiar with the Darboux frame, this is called the tangent normal vector. And this comes from the the Gauss divergence theorem, how it's called. Okay, very good. Now we have an equation and we have boundary condition. But there is something else, actually. There is something else. There is a geometrical constraint. Okay, so this equation is not complete if we don't add the following geometrical constraint. This is more complicated to explain. Now, if we take the curl of this vector field, again, we should get the Gaussian curvature here and the topological charge density. Should topological defects be present? Okay? Should topological defects be present, this quantity is not free, it's fixed, and is equal to the Gaussian curvature minus the topological charge density.
Luca, you could put probably also the boundary in there.
Here? Well, the boundary,
In the source, some term due to the boundary.
no, the term to the boundary comes only in the boundary condition, okay? Unless you have, like, say, defects on the boundary. And, okay, yeah. And there is a trick to solve this equation, okay? To solve this equation with this constraint, okay, there is a very nice trick, and it's the following. You introduce what I think Vincenzo called a geometric potential, okay, meaning you parameterize this gradient field here in the following way, taking the anti-symmetrized derivative of a scalar function called the geometric potential. Okay, this is like the anti-symmetric tensor. Now, if you do this transformation, if you do this parameterization, this equation is automatically satisfied, and this constraint is also automatically satisfied, provided the function phi obeys to the following equation. Laplacian of phi equal to topological charge density minus Gaussian curvature. Here I put little g just to indicate that this is like the Laplace Beltrami operator, so it's the Laplacian on a curved surface. Okay? Here we are. So here we have a framework. And this explains why this is called geometric potential, because it does express somehow, like the electrostatic potential, it expresses a disturbance, okay, in the orientation field, which is due to topological charge, either localized in the form of topological defects or distributed in the form of Gaussian curvature. Okay. Very good. So now we have changed the equation a little bit. This is already optimal now with respect to the orientation, okay, provided this condition is true. And I'm going to use the Dirichlet boundary condition. Okay, next we want to minimize the surface itself. Okay, now we have a surface that contains an optimal vector field in some sense, provided some conditions are satisfied. We would like now to minimize with respect to the shape, to the orientation itself, to the geometry itself. And to do so, we take the normal variation, okay? We displace points on the surface by a little amount along the normal direction of the surface itself. And, you know, calculating the variation of the area, okay, is very simple. Well, it's not simple, but is, you know, a standard exercise that you can find in all differential geometry textbooks, okay? This is going to be proportional to the integral of the mean curvature. And this is, by the way, why minimal surfaces have zero mean curvature, right? Because, you know, the area is minimized if h is equal to 0. But how we are going to deal with this, okay? Now we have to find the variation with respect to the normal to the displacement in the normal direction of this term, which has a lot of geometrical structure in it, right? There is the area term, there is the gradient, there is phi, which is a solution of a differential equation that contains information about the geometry. So how are we going to do it? Well, first of all, we know how to solve the Poisson equation, right? So let's solve it. And here is an important thing. I'm going to temporarily assume that there are no topological defects, okay? It's not required, but it makes now the proof a little bit simpler. We'll go back to the topological defects at the end, okay? And so the function phi is just equal to some convolution of the Green function calculated with respect to the metric of the surface times the Gaussian curvature. So this is very much like the electrostatic potential produced by a charge density that in this case is called kappa, K. All right. And the orientational energy now is really like the electrostatic energy. Okay, think about K as an electric charge density. Okay, and this is just electrostatic energy. Next, and this is the real trick, we're going to switch coordinates and introduce a system of conformal coordinates, or also called isothermal coordinates. Why this is important? This is like the key of this proof. Because in these systems, the metric looks Euclidean up to a scaling factor, which is position dependent. Now, why is this a big deal at all? Well, for the following reason. Because all the geometrical information is now contained in the scaling factor. Okay, so you are able to isolate the problem into a function. And in fact, for instance, the area can be expressed in this way, which is very familiar. The Gaussian curvature is actually has a very simple expression. Here is the Laplacian of the log of w divided by 2w. Here, by Laplacian, without the subscript g, is the Euclidean Laplacian. So, you know, the sum of the derivatives. Very well. Okay. The reason why I'm writing this is just to make this point even more clear. In this expression, all the geometric information that in the previous slide was all around, now is all contained into one function. And moreover, do you see the Gaussian curvature is the Laplacian of a log? Here there is a Green function, right? Some cancellation is going to happen. And in fact, if you now calculate the variation, it's super easy and gives you k times h times epsilon. So Gaussian curvature times mean curvature times displacement. And when you put all these things together, what you find is this equation. This equation has this is the variation. Now the corresponding variational equation has two solutions. One is the classic one, minimal surfaces. And then there is this other solution here, which corresponds to a surface of constant negative Gaussian curvature. Okay? Now, I think this is very cool. And there is a problem, though, that this really doesn't tell you anything about stability, about which one is going to actually minimize the energy, because, it could be that both of them are solutions, but maybe this one is going to have always lowest energy. So it's possible that if you make an experiment to get these weird surfaces of constant negative Gaussian curvature, you will never get, okay, because the energy is not sufficiently low. So what we can do is now to take a concrete example to see how this works in practice. And
don't you have any hyperparametric constraint on the enclosed volume?
no, I don't because I'm, okay, I see your point. So no, I don't.
So this would destroy that.
Yeah, but yeah, that's true. But I can imagine a system in which you can somehow relax these constraints. If you can, if you have an interface between two fluids, maybe you can invent a way to take the fluid out, right? If the volume is not constrained, or if you're
Kind of frame is fixed.
yeah, but okay. Let me show you the next example, and then I think this will clarify things. But yeah, you're right. I mean, the volume is not constrained. Now, what are our expectations? Okay, look at this term here. Okay, and I'd like you to invite you to think about the following ratio, the following dimensionless number. Okay, which is like the surface tension times, say, the area of the interface divided by this stiffness k, kappa. Okay, this is a dimensionless number. This one is the energy cost due to surface tension. This one is the energy cost due to the orientational elasticity. My expectation is that when this number is smaller than 1, more or less, the hyperbolic surfaces is gonna be energetically more convenient than the minimal one. Okay, when surface tension is dominating, so this number is large, then the minimal surface is going to be the preferred one. So this is my expectation. All right. Okay. So probably, we should expect a transition when something like that happens. And again, this is exactly true. This is something remarkable about this project was that all the simple intuitions turned out to be exact. All right. So I went back to consider the quintessential minimal surface, the catenoid. Okay. So this is a catenoid. And it snaps, right? Because if you pull these two rings apart, eventually it's no longer stable. It breaks into disconnected disks. And this happens when the distance between the two rings are comparable with the diameter. It's actually equal to the diameter of the rings. And this is the same experiment in slow motion. It's actually very cool. Now you don't even see that it's moving, but it's moving. Okay, so it's reducing. Somebody is like pulling this apart. It's reducing its area. And eventually, bam, it breaks. And here you can clearly see that the area, okay, of the two disconnected disks is lower than the area of the catenoid, because here is the leftover, right? This is like you have like this little droplet that contains the area that has been expelled. Okay, very nice. So just a reminder of the catenoid, very simple surface. It depends on a single parameter here, A, okay, which is related to the Gaussian curvature. Now, once you fix the boundary, the geometry of the boundary here, meaning the radius of the circle and the distance of these two circles apart, I'm going to call this R and this 2h. So h is actually the distance between the ring and the equatorial plane. Okay, then the parameter A is uniquely determined by solving this transcendental equation. The solution of this equation, however, does not always exist. Okay, it exists if the aspect ratio, h over r, is smaller than some number. And in fact, the catenoid becomes unstable when the aspect ratio is smaller than 0.5, about 0.5. So here is where it snaps and makes the two rings. Now, the same boundary actually can bound a surface of constant negative Gaussian curvature, which is like this sort of pseudo-spherical hyperboloid. I think this is the proper name, okay? Which again looks like more or less like a barrel, like a cylinder. In this case, the expression is not that different except for the z-coordinate. This is like an elliptic integral of the second kind. One important property of this surface is that it depends on two parameters, okay? Not just one, B and A. A is related with the Gaussian curvature, which is constant and negative. B instead is going to be related with the geometry of the boundary. So once you fix the geometry of the boundary and the surface tension and the physical parameters, the ratio sigma over kappa is going to give you the Gaussian curvature, while the parameter B and the geometry will be fixed by the aspect ratio of the hyperboloid. Here I put them into one another to show you the difference. And well, you can argue that they don't look that different after all. I mean, you know, this is the catenoid, the green one, the external one is the hyperboloid. I mean, I don't know, the catenoid is a little bit more slender in the center, but anyway, they are different from a geometrical point of view, okay? So what you can do, you can calculate the energy, okay? But now this, in this case, calculating energy is very simple, and it's simple because you have this rotational symmetry, right? And so if you have rotational symmetry, this quantity is going to depend only on the radial coordinate, this quantity is going to depend only on the radial coordinate, and the radial component of the spin connection is going to be 0. But then, if you calculate the gradient of theta with respect to this radial coordinate, you'll find that this is also going to be 0. So the optimal, what I'm saying is that on a surface like that, the optimal liquid crystalline texture is actually as constant orientation everywhere. Okay, as constant orientation everywhere. And this is actually not hard to imagine. And so, you know, the energy is simply given by this term. And, well, okay, it's an ugly expression, but you can calculate it analytically, okay? So this is the energy of the catenoid. This is the energy of this hyperboloid. If you want to be like completely sure that you're doing things correctly, you can even try to solve the variational problem, okay? So the Poisson problem, Gaussian curvature, Dirichlet boundary condition, okay? And this is something surprising that I wasn't really expecting. For both surfaces, the answer is the same. And in polar coordinates, it's actually this simple logarithmic function in which r is the polar distance from the axis, okay? Those are very different equations. They look different. In one case, the Gaussian curvature is constant. In the other case, it's not. The metric here is different and contains different terms. Nonetheless, these two Poisson problems with the Dirichlet boundary condition have the same solution. And given that we are in a math department, I'm not going to leave without making a conjecture. I think this is true for all topological cylinders. Actually, I think this is true for all surfaces of revolution. I don't know whether this will be useful or not, but. All right, so finally, let's compare the energies. Didn't change anything. Let's compare the energy. And, well, there is a line here that goes like this. And as you see, as our expectation somehow was suggesting us, you know, when this dimensionless number, sigma times r squared divided by kappa, is larger than 1, then the catenoid has lowest energy. But when this number is smaller than 1, then the hyperboloid has lower energy, okay? And as a matter of fact, the stability of this hyperboloid increases a little bit as you move close to where the catenoid is no longer stable because you are pulling apart too much. Okay. So this actually confirms that it's possible. I mean, you know, if we prepare the system in such a way that that we are in this region, we can really construct an interface that is a surface of constant negative Gaussian curvature. Okay, and this is, I mean, I don't know if you have other examples, but for me, this is like the first I know. All right, so let's make a summary. It's possible liquid crystalline interfaces can form surfaces of constant negative Gaussian curvature. Okay, and the Gaussian curvature is going to be given by this term, where sigma is the surface tension and kappa is the orientational stiffness. These hyperbolic interfaces are expected to be stable when the ratio of these two quantities that represents the energy cost associated with surface tension and to orientational elasticity is going to be smaller than 1, okay, roughly smaller than 1. So you remember the defects. What happens if you have defects? Well, if you have defects, here, okay, by R, really what I mean is like some measure of the system size. If you insert defects, you can actually run the same calculation identically, okay, and in this case, the Gaussian curvature is going to be given by eta minus the same term. So the topological charge density is going to appear here. Now, the topological charge density of isolated defects is a sum of delta functions, okay? So it doesn't make sense when you are within the core radius, and it's 0 outside the core radius. And so essentially, this is still true. I mean, this hyperbolicity still holds if you are outside the core radius. So a surface of a liquid crystalline surface interfaces with topological defects will look like some, you know, like an hedgehog, but not the defects like the animal, right? I mean, with all these spikes and so on. And this result, I must say, was anticipated in this paper by Frank and Carter of 2008, okay? Not in this way, the interpretation is not correct, but nonetheless, the result is there. All right, now, let's go back to the physics, okay? At this point, I'm going to ask you the trivial question. Let's imagine that they go to the lab, to somebody's lab, and I try to dip like a couple of rings into a liquid crystal. Am I going to get this bloody surface of constant negative Gaussian curvature? Well, let's see. Let's make some back-of-the-envelope calculation. So the orientational stiffness, okay, the Frank constant in 2D, I think is going to have dimension of kBt, right? Which is about 10 to the minus 14 erg. And the surface tension of a fluid at room temperature is about 10 erg over centimeter square. And so to get this, I need to get a system whose size is more than 1 nanometer. Okay, and so I don't expect this to be true. I mean, I don't expect the theory to hold at such a small scale. So nope, this is the answer. However, there is hope, because there are ways to make sigmas larger, the sigma smaller, and K in kappa larger, right? What are these ways? Well, so for instance, surface tension depends on temperature, and depends, in fact, on how close you are to the critical point where the two fluid mixes. And so, for instance, this is taken straight from Wikipedia, okay? And this is the phase surface tension versus temperature for benzene. And here you see at the critical point, the surface tension goes to 0. I'm not proposing to go to the lab and, you know, heat everything up at 580 Kelvin, because, you know, this will melt everything away. But I'm saying if you can approach the critical point, then there will be a way to decrease systematically the surface tension, maybe all the way to 0.
Wouldn't the thermal fluctuations make your interface? Unless the nematic stabilizes you. I don't know, actually.
I don't know either. Yeah, indeed. So in fact, I'm not. In fact, I don't think the good way of doing that would be with temperature, okay? But maybe with something else. Yeah. And let me tell you that in exadics, okay, which is, by the way, also the system where this theory applies more accurately, because the energy is precisely that one, you can actually, the Frank constant has a divergence as you approach the critical point for the solid exadic phase transition. Okay, this is a plot, it's an experimental plot by the group of Kame, okay, which really, you know, took the experiment on exadic to the next level. And this is like inverse temperature, and this is like Frank constant. And as you see, as predicted by the theory of Nelson and Alperin, you do have a divergence of the Frank elastic constant at criticality. Obviously, you are not going to reach infinite elastic constant. But for instance, this point here is 300 kBt, which is pretty high, right? So, I mean, my conclusion here, and this is really my conclusion, is that there are knobs, okay, that can be turned. So I think this is now a challenge for experimentalists. I've seen like amazing experiments yesterday and the day before. So if somebody wants to take the challenge, I'll be very happy to help. And thanks for your patience, and I will take your questions.
So presumably the anisotropy of the elastic constants of the pneumatic will have some effect on your conclusions?
the anisotropy in the, yeah, that's true. So, I mean, this is why I say that probably this is not like the right model for nematics, because in nematics is more subtle, and I wouldn't expect also the surface tension to be isotropic, right? But maybe for exotic the situation is a bit different. The fact that the energy is accurate for exotic was proved in a way that is much more rigorous than what I can do by people like Tom Powers and Philip Nelson and so on. So that's I would bet my money on that rather than nematics.
Maybe repeat the question.
Sure.
Luca, I'm just wondering if when you have either defects, as you mentioned at the end, or whether your surface cannot be continued, that there's a boundary, all these tricks that you're playing with conformal transformations may lead to terms that break conformal invariant because you're a fixed cutoff. Wouldn't that generate extra sources in your theory, like conformal anomalies that you need to worry about? It's a bit of a technical question, sorry, but it may have some observable implications.
You know, okay, so that's possible. Okay, that's possible. What I can tell you is that, for instance, if you take a system like this, so a boundary like this is going to be on a plane, okay, and you impose some tangential boundary condition, then the equivalent of this barrel is going to be something like this. And here, obviously, you have a singularity, you have a cutoff.
And that cutoff will be rescaled under conformal transformation.
And the cutoff will be rescaled on the conformal transformation. Yes, but
It breaks your invariance, so there's an extra term that you have to keep in the.
But you have to keep it in the equation, or you have to keep it in the boundary condition, though? Or you have a boundary condition on the defect core. So this is what I'm talking. I mean, you know, I don't know. I think it's a good question, but it's not obvious to me that they will produce extra sources. Okay, it could produce extra boundary conditions. Yeah. I didn't repeat the question, by the way. Sorry.
This may be a bit of a tangential question to your talk, but the initial functional that you put out, your norm of grad theta minus a squared, that looks like a functional that would appear in a gauge theory too. Have you wondered about that? And if so, would you comment on the gauge invariance of such a your solution?
I mean, so we are going a bit far from my range of expertise. What I can say about the gauge invariance is that, so if you have, how is it, something like this, okay, so that was somehow the energy density once you do like the tricks. This is invariant for the following transformation. And this is a gauge invariance. And my understanding is that what this implies is the O2 symmetry of the orientation order phase, meaning that you can rotate your local frame and the energy is not going to change. Whether this has like some more profound application in systems like described by the same gauge invariance, I don't know.
Which field theory is our geometry.
Okay. Okay, maybe when you have the transition to the hyperbolic surface, there will be associated to a particle, massless particle that I will call the Giomion from Luca Giomi. I don't know.